So hello everybody, this is going to be chapter 14 of Chemical Structure and Reactivity. So this by me, and here's the shout out list. Just hit me up if you want to be on the list. And also here's a list of people who have supported us on YouTube. So I want to immediately get into what this chapter will talk about. So this chapter will go a lot more into organic chemistry. If you remember some of my past lectures, chapter 11 was about the basics of organic chemistry, such as reactions with carbonyls and nucleophilic substitution reactions. However, this part will focus more on stereochemistry, which deals heavily with the symmetry of organic molecules. Oh yeah, and gerrymandering. Just saying, these lectures, they're based off a general chemistry book, a British general chemistry book, but this specific chapter's on organic. Maybe one day I'll make a series on Clayton or something. Yeah. But anyways, in addition to stereochemistry, we'll also discuss isomers, which are molecules that have the same molecular formulae, but have a different arrangement in space or connectivity. And in addition, for this chapter, I especially found it useful with visualization software such as Pymol. I think maybe Avogadro or like Autodoc tools. Those could also help. I'm not too sure about Autodoc tools. But another good way is to just get yourself one of those kits where you can build molecules out of these little spheres and little flexible bonds. So first off, I wanted to talk about what constitutional isomers are. And constitutional isomers are based on a concept known as a molecule's constitution. Now, this is defined as the way that all these atoms are bonded together. So, for example, in this image right here, right, we can see that each of these molecules has the formula C4H10O. However, if I go and look at this specific molecule, this is terbutyl alcohol. You can see that it's an alcohol, but if I look at this specifically, this one is an ether. And so there are different functional groups in these molecules, and they have the same molecular formula, just different constitutions. Now, the next concept I wanted to talk about is superimposability. So what do I mean by superimposability? Well, simply put, if you have two molecules, they are superimposable if you can have one molecule occupy the exact same space as another molecule. Now, a good way to understand superimposability is to look at your hands, right? So I have my left hand and I have my right hand. These hands are mirror images. But say, for example, I want to see, hey, are these hands superimposable? What I can do is I can flip my right hand, but no matter how I flip it, it will never look like my left hand exactly. And this specific concept is related to two types of isomers that I will get to in later slides, which are diastereomers and enantiomers. Now, I also wanted to talk about this image at the bottom. So this image was taken directly from the textbook, and this visually shows the concept of superimposability. So we can see that X and Y are molecules that are mirror images of one another. And so we can also see that we have something known as molecule Z. If we rotate molecule Z, then we can superimpose it or place it over molecule X. But it's impossible to place molecule Y directly on molecule X, which is directly related to the concept of enantiomers. Now, in addition to this concept of superimposability, I also wanted to briefly talk about another type of isomer known as conformational isomers. Not constitutional, but conformationals. And this is, this comes out of a concept where if you have two molecules, right? even if they do appear to be isomers in some way, you can superimpose them just by rotating around a single bond. Now, just to get into like a bit of valence bond theory here, according to valence bond theory, a single bond contains of one sigma bond, which is the head-on overlap of orbitals in the internuclear axis. If you watch my lectures on molecular orbital theory, this should be pretty easy to understand. But for those who don't understand, electrons exist in orbitals, which are just, well, pretty much clouds. And the overlap of these quote-unquote clouds create covalent bonds where electrons can be shared. And a sigma bond is just two orbitals going head-on-head on the internuclear axis, which is the axis that goes through the nuclei in an atom. I mean, in a molecule. And because of that, we can rotate the orbitals however we want, and that bond will still exist. And therefore, we get conformational isomers by just rotating around a single bond. For example, in this image I put here, this is a compound known as biphenyl, and this contains of essentially two benzene rings. So on this top image, we have we have both of these rings, both aligned. However, in this image, we can see that one ring is, I believe it's 43 degrees. It was like 43 degrees off the second ring in terms of rotation. And so we can just rotate, if you can see my mouse, we can just rotate this bond and pretty much we'll get the same conformation. Now, I also wanted to talk about the configuration of an isomer. So this is different from the constitution, which is how exactly the atoms are bonded, but a configuration simply describes how the atoms in a molecule are arranged in 3D space. So, for example, in this image right here, we can see that we have configurational isomers here. And that's because we have chlorine and we have a methyl, right? In molecule A, chlorine and methyl group, they're opposite of each other relative to this carbon-carbon double bond. However, in B, they are on the same side. And so the three-dimensional arrangement of these molecules are different, meaning that we get a configurational isomer. If you see the word conformer in a textbook, that also is an equivalent word for saying a configurational isomer. And so with this basic section on isomerism, here is a simple flowchart that I grabbed from Master Organic Chemistry, really good website by the way, about how to differentiate between two molecules and figure out if they're isomers or not. So we can see that the first condition is, do these molecules have the same molecular formulae? And of course, if they don't, well, they're automatically disqualified from being an isomer. However, if yes, there is a possibility that they can be isomers. Now, given that they're isomers, we can look at the same connectivity, and therefore we can determine whether it's a stereoisomer or a constitutional isomer. And finally, going on to that concept of superimposability, if we have non-superimposable mirror images, like your hands, right? Your hands are mirror images of each other, but you can't superimpose them, then we get isomers known as enantiomers. But if not, we get something known as diastereomers. Alright, so I'll let y'all post any questions that you have in Lectureland. I'll pause here for a bit. Okay, first question. Do we talk about isomers of ionic compounds? Do you mean coordination compounds? because I'm not too sure I've heard of isomers of ionic compounds. That's for sure. Okay, so next question, just to clarify, are stereoisomers 3D and constitutional isomers 2D? Hold up, let me also check this other comment. Ionic, well, you have to think ionic compounds are usually in like a crystalline structure, right? So we can get like different crystalline arrangements of ionic compounds, but not like the isomerism that we're talking here. Oh yeah, and constitutional isomers are 2D. And that's because they depend on atom connectivity, which we can infer from like a simple skeletal structure of an organic molecule. Okay, I see some more people are typing. Well, yeah. All right. I think that pretty much answers the Q&A session so far. So let's go on. So we already talked about configurational isomers or conformers, right? Now, let's imagine ethane, right? It's a simple alkane. We have two carbons, molecular formulas, C2H6, and overall, I mean, it's just an alkane, pretty boring. Now, here's something. Let's take something known as the Newman projection. Now, what is the Newman projection? I'll discuss this in this next slide briefly. So, what a Newman projection is essentially, what if we take some sort of molecule and look straight at the bond, right? And so, therefore, we can see that we have this I here and it's looking straight at this carbon-carbon bond. We get this Newman projection because we have this carbon bonded to A, C, and B. And in addition, we have this circle to differentiate between the front carbon and the back carbon. And this back carbon, as you can see, is bonded to D, E, and F. And so therefore, the Newman projection of ethane would look something like this, where you have the front carbon bonded to hydrogens, and you have that back carbon bonded to also hydrogens. Now, we can actually rotate these two carbons around that carbon-carbon single bond, and what we can use in order to describe this rotation is something known as the dihedral angle. I already discussed what the concept of this was back in the last chapter, but for those who don't know what the dihedral angle is, it is essentially just a way to measure rotation between two planes. And these planes contain certain bonds in a molecule. And as we can see, based on this dihedral angle, we get staggered and eclipsed configurations, and these change the relative energy. As you can see, if we have a staggered configuration, the relative energy will be at a minimum. But if we have it eclipsed, then it will be a maximum. Relatively 12 kilojoules per mole more energy. Now, we did look at ethane, but we can also look at butane using Newman projections. And with these Newman projections, we can get a lot more sophisticated view into how rotating butane around that central carbon-carbon bond will actually affect the energy. And you can see this graph is not similar to ethane, because ethane, you have pretty much a sinusoidal graph here. It just goes up and down, up and down, up and down. But with butane, you get a lot more nuanced configurations. So for example, you have anti with the lowest energy, but you also have gauche. And gauche, it's a little bit above the anti, but it's not anything like a maximum. All right. Now, I'm gonna keep talking about rotation here, and I want to briefly touch on amides. So, we know from valence bond theory that a pi bond is formed from the overlap of p orbitals. And so, in a double bond, we have one sigma bond and a pi bond. Now, pi bonds overlap side to side, and they're not on the internuclear axis. Therefore, if we rotate on the internuclear axis, what we'll need to overcome is we're going to need to overcome some sort of rotation barrier to break that existing pi bond. Because if we rotate this pi bond, those p orbitals, they won't be lining up anymore. Now, amides actually show a pretty interesting characteristic when it comes to like partial double bonds. And that's because of the resonance structure. As you can see, I have it in the bottom here. And you can see that because of this resonance structure, sometimes you can get a carbon-nitrogen double bond, or you can have the carbon-nitrogen single bond. And so we get a partial double bond characteristic in the molecule. And in addition, in terms of molecular orbital theory, as per my past chapters, that pi orbital, if we start thinking about molecular orbitals, that pi orbital is spread across the carbon, oxygen, and nitrogen. And in fact, when we actually experimentally look at the rotation barrier of an amide, it's between a single and a double bond. In fact, I looked up the data for this. The rotation barrier for a single bond is, well, not even that much. It's like 3 to 4 kilojoules per mole. Now, for an amide, it's something like 86 kilojoules per mole. But for a carbon-carbon double bond, that's going to be in the hundreds. And so we can see, because of this partial double bond characteristic, we get a rotation barrier that's in between. All right, so get ready for another type of isomerism. This is going to be known as cis-trans isomerism. And this is going to concern even more double bonds. So imagine that we have an alkene, right? We have a carbon-carbon double bond in the center, and we have certain groups that are attached to the carbons. Now, because double bonds have restricted rotation, we can have two groups either be cis or trans to each other. So, in a cis isomer, for example, we have this molecule right here. We can see in the cis isomer, the chlorines are going to be on the same side of that double bond. But in trans isomer, the chlorines are going to be on opposite sides. Now, when I first learned about cis-trans isomerism in my basic chemistry class, I thought, this pretty much is only related for alkenes, right? Well, wrong. It's actually related to coordination compounds such as cisplatin, transplatin, and in addition, it's also related to cyclohexane, because you can have substituents that can either be in an axial or equatorial position, and therefore you can assign cis or trans forms to these molecules that have cyclohexane in them. Now, we see that in this initial molecule here, right, this alkene, we have 2 chlorines and we have 2 hydrogens. But what if we had something like, I don't know, 4 chlorines, or we had a fluorine, a chlorine, a bromine, and an iodine? So we have 4 different groups. Now, because of this, we can't just use cis and trans. Instead, we have to assign certain priorities based on the CIP or Kahn-Ingold Prelog rules. And so these rules provide a way to assign priorities to these groups. So the first rule is going to be atomic number. So take, for example, I have hydrogen as a group, and I have like the methyl group, right? The methyl group will encounter carbon, right? And carbon has a higher atomic number. Therefore, we give it a higher priority. Now, the second rule in this image is the isotope rule. And so if we have isotopes of the same element, then the greater the mass, the higher priority it will get. So say, for example, we have deuterium and we have protium. Deuterium is just a deuterium's nucleus is just a proton and a neutron. Protium has just a proton. And of course, since deuterium has the greater mass, it will receive a higher priority than protium. Now, there's also a rule concerning multiple bonding, such as your double and triple bonds. And this states that if we have double and triple bonds, we treat them as multiple single bonds to the same atom. And in addition, if we have chains as groups, what we can do is we move outward along these chains until we can find a different point that we can use to differentiate when it comes to priorities. Now, going back to this new form of isomerism, EZ isomers, if the highest priority groups are on the same side of the double bond, we have a Z isomer. If not, we have an E isomer. All right. Now, we're going to go back to superimposability, everybody's favorite topic, and we're going to talk about what a chiral center is. Now, chiral centers are related to enantiomers and diastereomers. Now, a chiral center simply refers to a tetrahedral carbon, or in other words, if you're familiar with hybridization, an sp3 hybridized carbon with 4 different groups attached. Keep that in mind, different groups. So if we have 2 hydrogens attached to the same carbon, then unless that second hydrogen is something like deuterium, and the rest of the groups are different, then no, that carbon is not a chiral center. Now, quick side note, the authors in this book call this a stereogenic center, but you can also call it a chiral center, and whoever's learning about this from you, they'll understand. And we can see that we have this molecule alanine. Now, alanine is one of the 20 fundamental amino acids, and we have this chiral center right here, matter of fact. So we have this carbon right here. It's attached to an amino group, a methyl, a hydrogen, and pretty much the rest of the molecule. And these groups are all different, making this particular carbon the chiral center. And based on the arrangement of the groups, we can classify these enantiomers as L and D. Now, we'll also talk about another one aside from L and D, known as R and S. Now, based on a chiral center, we will go through a few steps to determine if it's R, which is rectus in Latin, and S, which is sinister in Latin. Rectus is just right, sinister is left. So first off, we need to identify our chiral centers. And once we have our chiral centers, we need to assign priorities for the groups based on our CIP rules. Then, what we'll do is, if you have something like a molecular modeling kit or like a molecular visualization software, what I want you to do is look at that lowest priority group, right? Group with the group number 4 in this particular example. We want to point that group away from us. So it's going straight away from us. And we can see that we can draw an arrow that goes from the highest priority group to the other group. So for example, in this particular molecule, alanine, we get 1, 2, 3, and CH goes around counterclockwise. Now, since the arrow is counterclockwise, we'll assign this S. But if it's clockwise, we'll assign it R. Now, another example of where we can label enantiomers as R or S is in limonene. So limonene, I talked about this in the sneak peek for chapter 13. Limonene is actually a pretty fun molecule, and its properties change based on stereochemistry. So, our limonene actually smells like citrus, and therefore, in artificial flavorings, we do use it in order to make things taste like oranges or any form of general citrus. However, for L-limonene, which has just the S chiral center, it smells more like pine. And we can observe this based on, let's see, yeah, we have our chiral carbon right here, and we'll see that this chiral center makes this an R as stereoisomer. So I'm gonna briefly pause here, just let y'all ask any questions about stereochemistry, or like enantiomers, that kind of thing. Yeah. Yeah, lots of molecules can change depending on stereochemistry. Yeah, that's true. Alright, anyways, going on to the physical properties of enantiomers. Oh yeah, true. In Lectureland, stereochemistry hater did say that L and D are related to plane polarized light, but we will be going over that soon. So, imagine that we put one enantiomer in an NMR IR machine, we get our spectra, and we put another enantiomer in these machines, and we also get spectra, right? Now, we pretty much get the same results. But if we get the same results, how exactly are we supposed to differentiate between these two enantiomers? Well, using plane polarized light, what we can do is if we have a solution of an enantiomer, we can pass a light ray through the solution. And because of the stereochemistry, that light will be rotated by a certain angle alpha. And for anyone who wants to get into the analytical side of this, we use an instrument known as a polarimeter to determine this rotation of light. So in fact, in this image right here, we have our enantiomers. And this value right here, alpha 20D, that just refers to light that refers to the angle of rotation from light that comes from a sodium lamp, pretty much. And you can see with S-valine and R-valine, these angles are directly opposites of each other. And so therefore, we can differentiate between these enantiomers just using that polarimeter. Now, here's a quick side note. Enantiomers are important in biology and drug development. And this is coming from somebody who is currently doing work in that. So, for example, you yourself, you are made of polymers that have chiral monomers. So, for example, the proteins that you're made of, or the protein that you consume, is made up of amino acids that have chiral centers. And in addition, in drug development, if researchers are trying to target some sort of enzyme that only accepts a certain enantiomer, if we don't have that correct enantiomer, or if the stereochemistry is wrong, then it won't fit into that binding site of the enzyme. All right. See, yeah. Now, going on about enantiomers, I want to talk about racemic mixtures. Now, what a racemic mixture is is it is a perfect 50-50 mixture, or roughly 50-50 mixture, of two different enantiomers. And therefore, because we have a pair of enantiomers in the solution, if we pass plane polarized light, because we have both these enantiomers in there, what we get is we don't get any rotation at all, pretty much. Now, if you remember chapter 11, the SN1 reaction involves pretty much two primary steps. Number one, you get the leaving group to leave and we get a carbocation. And second off, we have the nucleophile attacking the lone orbital of the carbon in the carbocation. Now, the carbocation can be attacked from two different angles. And so, given that the carbocation's end product has some sort of stereochemistry, then we can get two enantiomers being formed, and therefore we'll get a racemic mixture. Sorry, y'all, 1 second. Sorry, y'all, I need to manage the dog for a second. He's whining. Now, we only consider compounds that have one chiral center. But what if we add more? Well, if we add more chiral centers, what we'll get is a lot more stereoisomers. And in general, you can mathematically calculate how many stereoisomers there are using this formula. So for a compound with n chiral centers, there will be 2 to the power of n stereoisomers. Now, in addition, we will also get 2 to the power of n minus 1 pairs of enantiomers because of that. So we can see in this compound 3-amino-2-butanol, we have 2 chiral centers. And so, in addition to enantiomers, we have diastereomers. And these diastereomers, essentially, they have only one chiral center in terms of difference, right? So we have this particular molecule, chiral centers are R and R, and its diastereomer will be S and R. And its another diastereomer will be R and S. Now, in addition to diastereomers, I also want to introduce a class of compounds known as meso compounds. I accidentally said meso there. But what meso compounds are they are pretty much compounds that have multiple chiral centers, keyword multiple, but they also have some sort of symmetry in them that makes the overall compound achiral, and therefore they will not be optically active. And so, in a system with 2 chiral centers, for example, a meso compound will be R and S, or S and R. And that's because there's going to be some sort of symmetry that exists, such as a mirror plane. And matter of fact, linking this to molecular symmetry, if we have a plane of reflection, a center inversion, or some improper rotation axis, as we described back in chapter 3, then we can determine if we have a meso compound and if the molecule is achiral. In addition, there are also pretty fun compounds where they are chiral, but they don't even have any chiral centers. But that's just a brief fun fact. So, enough about stereochemistry. Let's talk about cyclic compounds. So, we observed previously that if we have molecules such as butane and ethane, they can take up various configurations because of rotations around their single bonds with these Newman projections, right? Now, rings can actually take up different conformations, just like carbon chains. Now, I also wanted to briefly introduce something known as ring strain. So, we have these cycloalkanes. So cycloalkanes, they're pretty much just alkanes, but you just try to force them into a ring. And so this first compound, compound A, that's going to be cyclopropane. And all of these carbons are tetrahedral. Well, in theory, right? But since we have 3 carbons, it should ideally be a triangle. Now, that is going to create a great level of strain. In addition to cyclopropane, cyclobutane is also a pretty strained compound. And that's because we're going to need some way to change these angles. And yeah, in addition, it's going to be hard for them to keep these 60-degree angles as in a normal equilateral triangle. And matter of fact, I do have a graph here that shows what ring strain looks like. So we have a minus enthalpies of combustion, and the greater the minus enthalpy of combustion, the more strained the ring will be. And so we can see that for cyclopropane and cyclobutane, we have a large amount of strain. But for larger rings, we do encounter a bit of strain for these medium rings, but for larger rings, they don't have to be strained as much. And therefore, they're pretty much just going to have no strain. Now, going on more about cycloalkanes, I wanted to talk about cyclohexane, which is a special one. And that's because this can go in different conformations. So when you see a cyclohexane molecule in your organic chemistry textbook, you might observe it in its chair configuration. However, you can actually twist it into these different configurations like boats, twist boats, and half chairs, which do have greater relative energies, but they do demonstrate how cyclohexane can be in different configurations. Now, if we just look at the chair conformation, right, we have both axial and equatorial hydrogens, which we can use to differentiate substituents. So for example, in this image labeled below, let's just look at A, right? That's going to be our chair configuration. The substituents that are labeled U are axial, and I accidentally put U there, but the ones labeled L are equatorial. Now, some substituents, if we substitute hydrogens for something else in cyclohexane, prefer to be equatorial. And we can quantify that using a value known as the A value. And we can see that the greater the A value, the more often you would find that particular substituent in the equatorial position. And so, for example, we have fluorine that's going to have an A value of 1.4, 64% equatorial. All right. Now, if we look at the T-butyl group, right, it has a pretty large A value of 20, and it's 99.97% in the equatorial position. All right. And so we're pretty much just going to end off the lecture there. So we have our key points. Let me just go over this. So to start off, isomers are defined as molecules that have the same molecular formula, but don't have the same structural arrangements or orientations in 3D space. And in addition, alkanes can have different forms of isomerism, from cis-trans to E to Z. Now, going on to chirality, enantiomers and diastereomers arise from these chiral centers, and we can classify them based on CIP rules. And finally, cyclic compounds exhibit ring strain, and cyclohexene can have both axial and equatorial groups. And just for a sneak peek for this next chapter, we're going to talk about, well, even more organic chemistry. So we're going to go into topics such as elimination reactions and the introduction of aromatic molecules. And these aromatic molecules, you can find them in your perfumes, your colognes, and even in your DNA. All right, so that's pretty much going to end off